We're recording. So welcome back, everybody. Today, we're going to finish up our discussion of capacitance. And next week, we'll discuss current and electrical resistance. And the week after that, it will be spring break. So that's just a preview of what's coming up. We have a homework assignment, which is going to be due next week. This is homework number 8. It's up here on the board. And as usual, there's a worksheet that goes with it. This is going to be due on Wednesday because of the test and the schedule being moved back by a day because of the test last week. Assignments are going to be due on Wednesday for the next couple cycles, but once we come back from spring break, we'll go back to having things due on Monday. Okay? Any questions on that stuff? All right then, so if you recall, the last thing we did on Monday was we started this problem, but we didn't finish it. So let's finish it up. We have this circuit shown here with a battery connected to a network of 3 different capacitors. And what we're going to do is solve for the equivalent capacitance of this network, which we actually did. That's the part we did on Monday. Does anyone have in their notes what the equivalent capacitance of that network was? 6 microfarads. It's 2 microfarads. Okay, so we worked that out last time. But what we haven't worked out yet is what is the total charge which is drawn from the battery? Remember, we call that Q in this notation. And then we also want to find the individual charges on each capacitor, which we're going to label Q1, Q2, and Q3. Okay? So now let's go through the work of finding those charges. Okay. So in order to do this, what I'm going to start with is the original circuit, which consists of 2 capacitors in parallel like this, which are C1 and C2. So C1 is the one on the bottom, C2 is the one on top in that parallel combination like this. And then that's connected in series with this one, which is C3. And that's all connected to a battery, which supplies the voltage, which we'll just call V. Okay, so I want to know what the charge on each one of these capacitors is, so let's actually label the plates. That's going to help us for what comes next. For capacitor 1, the plate that's connected to the positive terminal of the battery is going to have a positive charge on it, which I'll label as positive Q1. This one is going to be negative Q1, so that's just the positive and negative plates of that capacitor. Then up here, we have positive Q2, negative Q2. And for this guy, the negative terminal of the battery is directly connected to this plate, so this is going to be a negative charge minus Q3. The other plate is going to be positively charged plus Q3. So the point of doing this is just to label all the charges that we're eventually going to find. So we have them. Okay. So as we can see here, C1, C2 are in parallel, right? So flip back to your notes. What can we say about capacitors that are in parallel as far as the charges go? Okay, so the charges add together when we have capacitors in parallel. So charges add. Okay? And what that means is if we were to combine these into a single capacitor, which I'll call C12, the charge on that equivalent capacitor, which I'm calling Q12, is Q1 plus Q2. Okay? And it makes sense because basically the charge that's going into the combination is going to be split between these two, so they add together. Does that make sense? That's just generally true of parallel connections. What can we say about voltages in a parallel connection? They're the same, right? Because the logic behind that, if you remember, is we can go across the combination by going across the first capacitor down here, or we can go across the second capacitor up here, but we're starting and ending at the same 2 points. So the voltage doesn't depend on the path we take, so therefore it's the same across capacitor 1 or capacitor 2. So voltages are equal. So that means V1 equals V2. So we're not trying to solve for voltage here, we're trying to solve for charge. So do you recall how we write the voltage across a capacitor in terms of the charge that's on it? It's just Q over C. Okay, so that means the voltages are equal. Q1 over C1 equals Q2 over C2. Make sense? Okay, but in this case, can we simplify that? What do we know about C1 and C2? In this problem, they have the same value, correct? So C1 equals C2. So therefore, Q1 equals Q2. Make sense? They have the same voltage, same capacitance, therefore they have the same charge. Okay? And the total charge in the network is the sum of these two. That's the idea. Okay. So actually, let's do a little bit of work with that. See up here where we said Q12 equals Q1 plus Q2? Well, if Q1 and Q2 are the same exact thing, then Q1 plus Q2 is the same as Q1 plus Q1, right? Which is equal to 2 times Q1, which means Q1 is half of Q12. This is saying that since the charge between these two parallel capacitors is equally split between the two, each one gets half of the total. That's what this is saying, okay? Each one gets half of the total charge. That makes sense? All right. So then, remember, we simplified this. We redrew the circuit to combine 1 and 2 into a single entity, where now we have just a single capacitor, which we call C12, and it's clearly going to be in series with C3, right? Make sense? Now, if we label the plates, we label the charges on the plates. We have plus Q12 over here, we have minus Q12 over here. We have plus Q3 here, we have minus Q3 here. All right? So now we have C12 and C3 in a series combination. So the idea is if we're trying to solve for the charges on each capacitor, we need to remember what properties hold true when it comes to series connections. So do you remember? So what can we say about the charges? Are equal, right? If you have a series connection of capacitors, charges are equal. So that means Q12 is equal to Q3. And if we were to combine these into a single object, 1, 2, 3, that would have the same amount of charge. Okay? So all the charges are equal when you're in series, and that's equal to the total charge going into the network. That's what we're saying here. So we redraw this one more time. And now we just have a single capacitor with the equivalent capacitance C123. And the charge on its plates is positive Q123, negative Q123. Make sense? Okay, so therefore, we can go ahead and solve for Q123. So now that we've reduced this down to a single capacitor, what would the charge on its plates be? How could we solve for that?
C123 times V.
Yeah. Because the voltage applied across the plates is V, and we know that the charge on capacitor plates is equal to the capacitance times the voltage applied. So just Q equals C times V applied to this situation gives us. All right, so now we're going to take the result that we came up with last time, right? What was the equivalent capacitance of these three combined into a single object?
2 microfarads.
That was 2 microfarads, right? So we worked that out last time. Micro is 10 to the minus 6. So 2 times 10 to the minus 6 farads. And a farad, what's the equivalent unit there? Do you remember?
Coulombs per volt.
Coulombs per volt. And what's our voltage? It's 4 volts. So what we have is 8 times 10 to the minus 6 coulombs of charge, or 8 microcoulombs of charge. That's the total that's being drawn from the battery, okay? But here's the thing. We can now use this to calculate the individual charges. Because as we said over here, we have, when we analyze the series connections, Q3 is equal to this charge. Okay, so Q3 is equal to 8 microcoulombs. We don't even need to calculate that. We already knew that Q3 was equal to Q123. Okay? Also, Q12, that's equal to this, which is 8 microcoulombs from up here. But if we want the individual charge, we have to use this result that we derived. Q1 is equal to a half of Q12. So it's equal to a half of 8 microcoulombs, which is 4 microcoulombs. So capacitor number 1 has 4 microcoulombs of charge on its plates. Capacitor number 2, as we worked out over here, Q1 is equal to Q2. So Q2 is the same as Q1, which means it's also 4 microcoulombs. Okay? So if you understand the rules of how capacitors combine in both series and parallel, you can basically solve for any network of capacitors that are combined in those ways, okay, and find the individual charges, okay? So we'll probably do another example of this before the lecture's over. But any questions so far? Okay, so that was that example. More like this on the upcoming homework. Solving circuits is going to be a big topic that we're going to be dealing with over the next month or so. But let's move on to the last part of this lecture, which is dielectrics. I actually briefly explained what a dielectric was, if you recall. Does anyone remember what a dielectric is?
It's a material that increases the permittivity.
Yeah, so it's a material that we place inside of a capacitor between the plates. It increases its capacitance, is another way to say that, yeah. So let's get into this. So most of the time, we're not going to be dealing with so-called vacuum capacitors. So up until this point, the assumption has been whenever we have a capacitor, there is some amount of charge on the 2 conducting plates, but in between the plates, there's just empty space. There's just a vacuum. You can certainly design a capacitor that way, but in the real world, that's not usually how it happens. Usually, you're going to use a dielectric material to place in between the plates. Now, here are a few reasons why you would do that. So here are some of the advantages of using a dielectric. So first, dielectrics typically will undergo electrical breakdown much less easily than the air. Okay? So in other words, it takes a stronger electric field in that material before it starts to act like a conductor and discharge the capacitor, basically. Okay? Of course, if you place some kind of material, a layer of insulating material between your 2 conducting plates, it just ensures that they're going to be separated. So in a capacitor, typically the separation between the plates is pretty small. So it is a problem if the plates end up touching each other, right? Because if I have some positive charge up here and some negative charge down here, and then the plates touch, guess what? They're just going to discharge. You're just going to neutralize both plates. You don't want that. Okay, you want the charge to be held on the plates. So by putting an insulating material in between, we just ensure that they don't touch and the capacitor doesn't discharge. So the last reason is that dielectrics will actually increase your capacitance. Okay, so if you compare these two situations, a capacitor just filled with vacuum. Let's call the capacitance of this one C0. That's typically how we're going to label this. C0, 0 indicates a vacuum between the plates. And then we compare that to this capacitor, which has some kind of dielectric material in between the plates. Now, there's a value called K associated with this material. It's called the dielectric constant. And what we'll see is the value of the capacitance here is greater by some amount, and it's given by this formula. So C, this is the capacitance with the dielectric present, is equal to K, which is just a numerical constant. It's a dimensionless constant. It doesn't have any units, just a pure number, times C naught, which is the capacitance with vacuum in between plates. So for example, if C is equal to 10, that's telling us that it increases our capacitance by a factor of 10. If it's equal to 100, we increase our capacitance by a factor of 100. And this number K is just a property of the material. So every material has a unique value of K. Okay? So let's take a look at some of these K values, okay? So if you look in this table, I'm going to show you the dielectric constant K for a number of different common materials. And we're going to start with a pure vacuum. So in a pure vacuum, K is by definition 1, because your C value is exactly the same as having a pure vacuum between the plates. If you have air, okay, and air kind of depends on the density of the air and the pressure of the air, but air at 1 atmosphere, so the air we typically experience at sea level, its pressure will have a dielectric constant just slightly greater than 1. It's 1.0006. Okay, so it's just a little bit greater than that of a vacuum. If you use a material like paraffin, now we're up to 2. And you can see a whole bunch of other different materials here. I'm not going to list them all. Okay, but there's also something called the dielectric strength that I want to point out. Okay, so the dielectric constant K, remember, that tells you by what factor does placing that material in between the plates increase our capacitance. So if you like, you can rearrange the equation to say this. K equals C divided by C naught. It's the ratio of the capacitance with the dielectric to your capacitance without the dielectric. So just what factor does it increase by? That's K. That's what we call the dielectric constant. The dielectric strength is something different. The dielectric strength is the maximum E field that the material can withstand before it undergoes electrical breakdown. Okay, so remember, when electrical breakdown occurs, the material begins to act like a conductor, and that's just going to discharge the capacitor. Okay, so we don't want to reach the dielectric strength of our material, because essentially we'll just be breaking the capacitor at that point. Okay, and so you want your material to have a very large dielectric strength so it can withstand very, very strong E fields. You can put more and more charge without breaking your capacitor. Okay, that's the idea. So if we take a look at the dielectric strength of various materials, we'll start with air. So we've seen this one before, right? For air breaks down and starts to act like a conductor once the E field strength becomes about 3 times 10 to the 6th power volts per meter or newtons per coulomb. Remember, these are the same unit. Okay? But look at these other materials. They have a much larger dielectric strength, right? Like, for example, paraffin, the dielectric strength is more than 3 times larger than that in air. So that means in paraffin, you can withstand about 3 times the E field strength as in air before it breaks down. And that's a desirable thing for a capacitor. Does that make sense? So you see a table quite like this in your textbook. You might have to look up some of these numbers for the homework. Okay?
Why doesn't water have a dielectric strength in it?
So this is going to depend heavily on like the mineral content in the water. Yeah. What kind of ions are floating around in there? Yeah. Let's do an example using this idea. So if you take a look at this table, okay, So let's say we have a parallel plate capacitor and it consists of two circular plates. Each one has a radius of 75 centimeters. And the separation, the distance between them is 0.125 millimeters. Okay, so at first, we're going to suppose that in between the plates we just have air, where K is basically equal to 1. It's a little more than 1, but we're just going to use 1 here. It's close enough. And the dielectric strength is 3 times 10 to the 6 newtons per coulomb. So my question for you is, what is the maximum charge that we can hold? So by maximum, I mean, what's the most charge we can put there before the air in between the plates breaks down and then it just discharges the capacitor through the air, right? That's the maximum charge it can hold. So we'll do that. Then we'll ask the question, let's say instead of just having air between the plates, we fill it with paper. Okay, so paper has a dielectric strength of 15 times 10 to the 6 newtons per coulomb, and it has a dielectric constant K of 3.7. So in that case, what's the maximum charge it can hold? What we're going to find out is with this dielectric material in between the plates, you can hold a lot more charge. That's the point. So we'll see exactly how much more. Okay, so let's go through this. So there are two things we're going to do here. First, we're going to remember that C, the capacitance of a capacitor is given by K times C0. So we take the dielectric, move that down. We take the dielectric constant K for our material and multiply by C0, which is the capacitance, assuming just a vacuum in between the plates. Okay? Now this is a parallel plate capacitor, right? It doesn't have any other type of geometry like a cylinder or something. So can anyone tell me what is the formula for the capacitance of a parallel plate capacitor?
A epsilon naught over D.
Yeah, so this is A epsilon naught over D. This is a parallel plate capacitor. That's where that formula comes from. Okay? Okay, the other thing we can see is that Q, the charge that's going to be held on the capacitor plates, is equal to C times V. Okay? So we're going to take a few steps, but hopefully you see the roadmap here. We have a formula for the capacitance, and we use that in this formula for the charge. And we can directly calculate the charge if we have this formula properly worked out. But the one thing we don't know right now is V. Okay, we don't know the voltage. So what I'm going to do next is try to relate the E field, that's the electric field strength inside the capacitor, to the voltage across the plates. Okay, because we know the E field, we know what we're going to plug in for that, but we need to relate that to a voltage somehow. Does that make sense? So let's do some work on that. So here are the two parallel plates. Let's say I'll have plus Q on this side, minus Q on this side. What I want to do here is try to come up with some kind of formula for what the voltage across the plates is, so we can use that. So, real quick, what direction is my E field pointing between the two plates?
To the right.
Yeah, it points from positive to negative, if you recall. That's my E field, and we can assume it's basically uniform in between the two plates, which is a good assumption if the plates are big compared to the separation. So we'll assume E is uniform. Now, how do I calculate a potential difference between 2 points? Well, if you recall, delta V, the potential difference between 2 points, is given by minus E dot dl, integrated over some path. So I'm just going to use that idea here. I want to know the potential difference between the two plates. So if I integrate over the E field in between the two plates, from one plate to the other, I should be able to get the potential difference I want, okay? So let's try this. Let's take the path that starts here and ends here. Doesn't really matter which way I go, as long as I'm going from one plate to the other. But let's just do this. So my DL vector would be this one right here. It'd be going from the negative plate to the positive plate, okay? Now, does anyone remember, since we have a uniform E field, we really don't need to go through all the work of doing the integral in that case. Do you remember how this simplifies when you have a uniform E field? Yeah, so it's technically, it's minus magnitude E times D, which is the distance we're traversing, times cosine of an angle. Does anyone remember what the angle represents here? That's the angle between your E field and your path. So in this case, we chose a path that's going directly against the E field. So that's going to be cosine of 180. Make sense? So to write this in a more simple way, cosine 180 brings a factor of -1 out, cancels with that negative factor. So I'm going to write this in the following way. V is just equal to E times D. Because in previous chapters, we've written potential differences as delta V. Once we start analyzing circuits, the notation just changes. I know this is a little weird, but this is a notation change that happens in the textbook and pretty much any other source you read. We just call that V, we drop the delta, okay? But we're talking about the potential difference between the plates. We're talking about the magnitude of it in this case, okay? All right, so is everyone good with that? So here's what we're going to do. Q, that's how much charge we have on the plates. That's equal to C times V. C, that's equal to K, our dielectric constant, times A epsilon naught over D. And then V is the electric field strength in between the plates, also times D. Okay, so we just substitute in for C and substitute in for V, and we get this. Okay, how can I simplify that? Yeah, just cancel out D. So we have K, A, epsilon naught times B. Now let's just be really careful about, what numbers are going in here. K is, of course, the dielectric constant. So if we're talking about air, we're going to use K equals 1. E, this is going to be our dielectric strength. That's going to be the maximum E field that our capacitor can withstand. So of course, if we plug in the maximum E field here, what we'll get out is the maximum possible charge that we can hold. So we're going to do this for the two cases, right? One is for air. So we'll do that now. For air, Q max is equal to, okay, so I have K. What's the K value for air once again? 1. That's just 1. What am I going to use for the area? These are circular plates, so we use pi r squared. In this case, the radius was 75 centimeters. So 0.750 meters squared. That's the area. Epsilon naught, what's the value? It's 8.85, 10 to the minus 12 coulombs squared over Newton meters squared, like this. And then E. That's our dielectric strength again. So for air, what goes in for E?
Is it 3 times 10 to the 6?
Yeah, that's where we have 3 times 10 to the 6 newtons per coulomb. That's the dielectric strength. Okay? Could someone crunch those numbers for me and tell me what it comes out to? You can see the units come out in coulombs, right? Because meters squared cancel here and here, newtons cancel here and here, and then we just are left with coulombs. So what does it come out to?
the negative 5.
Yep, so it's 4.7 10 to the minus 5. That's the maximum charge we can hold if the capacitor is filled with air. Okay, if it's filled with paper, we're just doing the same calculation, but different values for K and E are going in there because it's a different dielectric constant and a different dielectric strength. So the K value for paper is what I gave you. It's 3.7. The area stays the same, so that's pi times 0.75 meters squared. Epsilon naught stays the same. 8.85 10 to the minus 12 coulombs squared, newtons meters squared. And then the dielectric strength, that was 15 10 to the 6 newtons per coulomb for paper. Okay? So can someone crunch those numbers?
2.35 to negative 4.
Get something different.
I got 8.7 or 8.7 times 10 to the negative 4.
Yeah. So, well over 10 times greater than before. Okay? Does that make sense, everybody?
Yes, Professor, I have a question. Previously, you said for the parameter, the capacitance is equal to A epsilon naught divided by E. But then I don't know why you put K in the form.
Because it's A epsilon naught over D, assuming we're filled with a vacuum. You multiply by this K constant when there's a dielectric present. So it goes back to here, right? Your capacitance is equal to K, your dielectric constant, times C naught, which assumes a vacuum. So K just tells you what factor you need to multiply by in order to get the correct capacitance, given that it's filled with some material and not vacuum. Okay, so all I did was I took that K constant multiplied by our previously found formula. Okay? Anything else?
Can you move it down? Thank you.
Okay. So let's keep going with this. You know, what I want to get across next is, you know, why is it exactly that when we put a material, dielectric material in between the plates of the capacitor, that it increases our capacitance? Like, why does C actually go up? I want us to get an understanding of that. And then I also want us to get an understanding of some of the microscopic details of what's going on at the atomic level in this dielectric material. Okay, so that's what we're building up to. But let's start here. What is the effect of adding a dielectric when you keep the voltage constant? That's the question we want to answer here. Okay, so here's the scenario. We have something really simple. It's just a capacitor, and it's hooked up to a battery. And as we know, when you do this sort of thing, you create charges on the plates of the capacitor, plus Q and minus Q. But in this initial scenario, we're going to imagine that there is no dielectric in between the plates of the capacitor. So in other words, we're just going to imagine it's filled with pure vacuum. All right? So, of course, in that scenario, I'm going to call the capacitance C naught. That means there's just a vacuum in between. And the charge is going to be Q naught. So it's going to be plus Q naught up here, minus Q naught down there. All right? Then I want you to imagine that while we're still hooked up to the battery like this, we place a dielectric material in between the plates of the capacitor like this. So we charge it up with the battery, then we add the dielectric. That's the process, okay? So I'm going to claim that what's going to happen is we'll get a new amount of charge on the plates. We'll draw even more charge off the battery, which will go onto the plates in this scenario, okay? And that new charge, I'm going to call that Q without the subscript 0, okay? So Q naught, C naught, that's with no dielectric. QC, that's with the dielectric. All right? You all good on that? So the way we're going to figure out what happens here is actually pretty straightforward, because you see, this entire time, we're connected to the same exact voltage source. We're connected to the same battery. So even though we add the dielectric, the voltage across the capacitor stays the same, because that's just determined by our battery. Okay, so what stays constant here is the voltage. It's important to see that. Does that make sense? Now, can anyone remind me, what do I use, or what can I use as a formula for the voltage across a capacitor? It's Q over C, right? So the voltage to start off would be Q naught divided by C naught, correct? And then the voltage at the end would be Q over C, but those are the same voltage. That's the idea. Okay, so let's just work out the consequence of that real quick. So because voltage is constant, we have Q naught over C naught equals Q over C. So what I'm going to do is solve for Q. That's going to be C divided by C naught times Q naught. But if you recall, C, that's our capacitance with the dielectric material, is K times C naught. And that's multiplying Q naught. So to simplify, Q is equal to K times Q naught. So if we keep the voltage constant and we add a dielectric, that increases the charge on the plates, okay? And it increases the charge by a factor of K. That's what we're seeing here. That make sense? So the charge goes up by a factor of K. That's our dielectric constant from before, okay? So that's the result. And there it is. So Q, charge on the capacitor with our dielectric present, equals K, the dielectric constant, times Q naught, which is the charge on our capacitor plates without the dielectric present. Okay? All right, so let's try a slightly different scenario, okay? Let's see what the effect of adding a dielectric material is, but we're not going to keep the voltage constant in this case. We're going to keep the total amount of charge constant. Okay, so it's a slightly different scenario, but we're going to analyze it in a pretty similar way. So here we go. This is the scenario. We're going to take these three steps. First, we're going to take a capacitor that has no dielectric in between its plates, and we're going to charge it up by connecting it to a battery. Okay, and when we do that, we get charge plus Q naught minus Q naught on the plates. So that's just the same starting point as before. But then we're going to do something different in the second step. We're going to disconnect the capacitor from the battery. Okay? So same capacitor as before, but now it's just disconnected from the battery. But it has that same charge on it from before because it acquired that charge by being connected to the battery. Okay? But then in the third step, we're going to add the dielectric. So we're just going to slide in between those two plates this dielectric material. And what we'll see is the charge stays the same. For the simple reason that the charge has nowhere to go. Okay? It's pretty much just stuck on the plates. If it were connected to a battery, it could move through the circuit and the charge could change. But if it's disconnected like this, the charge is basically fixed because it has no path to move on or off the plates. Does that make sense? All right, but what will change, as we'll see, is the voltage across the plates. So what we're looking at here is what is the effect of adding the dielectric when the charge stays the same, but we allow the voltage to change? That's the question here, okay? So let's go through that. Here, let's do that on the same paper, actually. So now we're doing this other scenario where the charge is constant. So for a capacitor, how could I write the amount of charge present in terms of C and V? Q is equal to Q is equal to just C times V for capacitor, okay? But the idea here is, initially, we're going to call that C naught times V naught, because this is before we've added the dielectric, okay? And then after we've added the dielectric, we're going to call that C times V, okay? Does that make sense? So we're just saying the charge initial equals the charge final before and after adding the dielectric, because it has nowhere to go. Remember, that's the idea. So V, what does that equal to? Let's solve for it. That's C naught divided by C times V naught, correct? Okay, well, let's just take one more step. C naught divided by C. C is equal to K times C naught. That's the idea. We increase the capacitance by some factor K here, and that's multiplying V naught. So therefore, the voltage is V naught divided by K. Okay? So if we keep the charge constant and we add a dielectric, we're actually reducing the voltage across the plates by a factor of K. You see that? Because K goes on the bottom. Now, I want to remind you, this is something we derived before, but if you have a parallel plate capacitor, there's basically a uniform E field in between, and the voltage across the plates can be written as E times D. It's the electric field times the distance between the plates. Remember this? We just did this? Okay. So I hope you can see that E and V are just related by a factor of the distance. So therefore, if my voltage drops by a factor of K, guess what? My E field is also going to drop by a factor of K. That make sense?
This is the voltage between the two capacitors?
This always, okay, in the context of a capacitor, when we say V, we're always referring to the voltage across the two plates, from one plate to the other. Make sense? So the E field is going to be reduced by the same exact factor. So they both go down by a factor of K. Does that make sense? Okay, so here, let me just say one more thing about this real quick. C, the definition of capacitance, right, is Q divided by V, correct? So we just took a look at these two different scenarios. One in which voltage is held constant, and this other in which charge is held constant, okay? So if we look at the first scenario, we're keeping V, which is on the bottom, exactly the same, right? But we found that we end up increasing the charge Q by some factor. So if we keep the voltage the same while increasing the amount of charge we can put on the plates, we've just increased the capacitance. We increased it by a factor of K. The other scenario is this. If we hold the charge constant, the voltage goes down. So if Q is constant and V is reduced, my capacitance is still going up, right? Because I'm reducing the denominator here. So either way you cut it, the point is, by adding this dielectric material, you increase the capacitance by this factor K. Okay, that's the idea. Yeah?
Is there ever an instance where you want to be specific about whether it's increasing the charge of the voltage, or does it really matter?
So it'll depend on exactly what's going on. Usually we're not going to do problems like this where you insert the dielectric midway through. That's kind of a unique scenario, which I'm just trying to use to illustrate these points. But yeah, it'll depend in that case. Okay. But usually we'll just have a capacitor that already has some dielectric in it, so we know how to use the formulas to describe its capacitance.
Got it.
All right. All right, so this one is just one of these examples, okay? Here's the scenario. We're going to remove a dielectric from a capacitor in this case, all right? So in this example, we're going to consider this very simple circuit shown in the diagram. We have a battery with a voltage of 100 volts, and we have a capacitor that has plates with area 4 square meters separated by a distance 4 millimeters. And initially it's filled with a dielectric with a K value is 3.4, okay? So now, we're gonna charge that capacitor up by connecting it to the battery. That's the first step. The second step is we're going to disconnect that capacitor from the battery. And then the last step is we're gonna remove the dielectric. Make sense? So these are the steps. We're gonna do two things. We're gonna find the energy stored in this capacitor before we remove the dielectric. So in this picture, how much energy is being stored? And then in this picture, how much energy is being stored? We'll get both of these, okay? And then we'll see that there's a difference, and we'll try to understand why there's actually a difference there, okay? Now, let me ask you this. Between this second step and this third step, what's remaining constant? Is it the charge on the plates, or is it the voltage across the plates?
The charge.
All right, and why is that again? Yeah, basically it has nowhere to go. There's no path for it to move anywhere else, so it has to stay on the plates. But the voltage could potentially change. So the charge is going to be the same between these two cases, okay? Important to be able to see that. Okay, so with that in mind, we know the charge stays the same. So let's find out what that charge is, and let's use it to calculate the energy stored in each of these cases, all right? So let's do that. Can anyone tell me real quick, what is a formula for the energy stored in a capacitor? This is given by uppercase U, if you recall.
1 V squared.
Q squared over 2C, that's right, yeah. So basically, we're gonna go ahead and find out what Q is, which again is not changing between the two scenarios. And then we'll figure out what C is in each case. C is going to change, isn't it? Because we're removing a dielectric material, right? So let's start by finding Q. Let's find the charge on the plates. How should we go about finding the charge on the plates? Any ideas?
We could use the previous formula, K epsilon naught EQ.
All right, so yeah, we could use that. I want to just go back to something more basic, all right?
Okay.
Q is equal to C times V. Because in this case, we know the applied voltage, right? And we can calculate C. We have all the information we need to do that. So this is probably the most straightforward way to go. So C, what is this equal to? Well, it's equal to K times C naught, where K, our dielectric constant is 3.4, and C naught is equal to A epsilon naught over D. Okay? So in this case, we have 3.4, and then we have times A. The area of the plates was
4 meters squared, right?
4 meters squared. Yeah, sorry, I was trying to find that. 4 meters squared, epsilon naught, 8.85, 10 to the minus 12. Remember, this can be written as farads per meter. That's going to be useful here just to see how everything works out. And then the distance between the plates was 4 millimeters. So that's 4, 10 to the minus 3 meters. Okay, now just to be clear, this is with the dielectric because we're multiplying by our K constant. Can someone tell me what this works out to? Did you remember to multiply by this part?
I didn't know. 3 times 10 to the negative 8.
Yeah, so I'm gonna write this as 3.01, where we'll keep 2 sig figs on that. And yeah, it's times 10 to the minus 8 farads. That's with our dielectric, what the capacitance is. Now let's actually do it without the dielectric. That's C naught, because we're gonna need to know this as well, okay? In this case, I'm basically just multiplying by 1 times A epsilon naught over D. Okay? So in this case, just think of this as 4 square meters times 8.85, 10 to the minus 12 farads per meter, divided by 4 millimeters, which is 4, 10 to the minus 3 meters. So this is what comes out to 8.85. 10 to what power?
10 to the negative 9.
10 to the negative 9 farads. And just to be clear, this is without the dielectric. Okay? So we have the 2 C values. Now, just going back to the slide. When we charge this up using the battery, the dielectric is present, right? So to find Q, we're going to do V times C, not V times C naught, okay? Make sense? So the charge on the plates is equal to C, which is 3.01 times 10 to the power minus 8. That's farads. Farads is coulombs per volt. And in this case, the voltage was just 100 volts, which means our charge is 3.01 10 to the minus 6 coulombs, because you're just multiplying that by 100, right? Takes 10 to the minus 8, brings it to 10 to the minus 6. Okay, so now that we have the charge on the plates, which stays the same, we can get the energy stored in each scenario, right? So with the dielectric present, that's going to be U. So here, energy stored with dielectric. Let's do that. That's going to be U equals Q squared. That's 3.01 10 to the minus 6 coulombs squared, divided by 2 times C, which is this value, 3.01 10 to the minus 8 farads. I think I showed you last time how this works out unit-wise to units of joules. So it's an energy, we have SI units in, we get the SI unit of joules out. What does this work out to? What's the number?
Um, 1.50 times 10 to the negative 4.
Okay. So that's the energy stored with the dielectric. Now let's do without. So this is the last step where we remove the dielectric. Now that's gone. So U is equal to the same charge as before. Remember, that's not going to be able to change. So that's 3.01 10 to the minus 6 coulombs squared, divided by 2 times C, and now our capacitance is this value, which is 8.85 10 to the minus 12 farads. Can you crunch those numbers for me?
Um, 1.505.
Get something different for that.
5.12 to 10 to the negative 4.
Yeah, 5.1 times 10 to the negative 4 joules. So interestingly, something's happened here. Initially, the dielectric is present, we charge it up, and it stores this much energy. Then we remove the dielectric, and now it's actually storing more energy than before. There's a reason for that. You have a question?
Yeah, should it be to the -9, not to the -12?
Oh yeah, I'm sorry about that. Yeah, it's -9. That's my bad. Yeah, good. Yeah, but you do get this number. It's -9. Yeah, I was confusing that with epsilon naught for a second there. All right, so let's try to explain this energy difference, okay? Now, just as a really broad physics principle, if you have some kind of system, doesn't matter what it is, and you are changing the energy of that system, fundamentally you have to do work to change the energy, right? So simplest thing in the world is lifting something up, right? If I want to change the potential energy of the stapler, I have to do work by moving it up into the air. So because I've expended some work, I've increased the energy. That must be what's going on here. In order to take the dielectric out, it actually requires some work. It doesn't just come out easily with no resistance. It actually, as we're going to see, because of the charges on the dielectric, it's going to take some force to pull it out, and you'll have to do some work. And that explains the energy difference here. Okay? So, any questions on that? Yeah, go ahead.
If you have like two different scenarios, like not that you take it out, but you test that like same thing, is there an energy difference, or is it only from taking it out?
So I'm not sure what scenario you have in mind.
Gotcha. Like, if we aren't taking the dielectric out,
Yeah.
but rather just like two different scenarios, or one is with a vacuum, one is with the dielectric, do they have the same energy, with the same like voltage and charge?
No, because basically you'd have how to say this. One way to see this is U is equal to a half CV squared, right? So if the voltage stays the same, but you're changing C, you're changing the energy on it. Yeah. Okay. So now let's get to the microscopic level picture of what's going on in the dielectric. So far, I haven't fully explained this picture. I've just claimed that, there's this K constant, which tells us by what factor things like the capacitance change. But now we want to see why that's happening on a microscopic level, because this is the ultimate explanation for that. All right, so do you remember this kind of picture from the very first lecture we did?
Yeah.
These are what we call polar molecules. Remember that? So, polar molecules. In a dielectric, basically, you have a whole bunch of polar molecules. That's fundamentally what you're dealing with, okay? And that means that within the molecule, even though the molecule itself is charge neutral, there's a separation of the charges. So there's a positive end, and there's also a negative end to that molecule. And of course, if we're putting this dielectric material inside of a capacitor, where there's a charge on the capacitor plates, it's going to be inside of an electric field, right? There's going to be an electric field basically going across these molecules, okay? And because of that, the molecules are going to respond in a certain way that I want to show you. So let's start with this. Let's say we just have a dielectric material that has a bunch of polar molecules, and there's no electric field being applied. Okay, so the E field in the region where we have these polar molecules is equal to 0. If that's the case, they're just going to be aligned in completely random directions. Okay, molecules, because of thermal energy within those molecules, they're just going to be randomly jiggling around. So any orientation they take on is quickly going to be changed by just bumping into another molecule. It's going to just be a completely random mess of orientations. They're not going to be in any sort of organized way. But if we're to turn on an electric field, let's say by putting these molecules in between charged capacitor plates, then they're going to want to align with that electric field. Okay? So in this picture, I'm showing you the electric field we apply going to the right. Okay? So do you remember for a negative charge, what direction is the force that a negative charge feels?
The opposite of the electric field.
Yeah, a negative charge feels a force opposing the electric field. What about a positive charge?
The same, right?
It's going with the electric field, yeah? So the positive end of these molecules is going to want to face the electric field. The negative end is going to want to face against it, which makes the molecules align like this. The positive end going towards the E field, the negative end going against it. Okay, so with no external E field, molecules are randomly oriented. With the external E field, they're aligned with it. Does that make sense? This is really important to what's going on here. And, okay, let's look at another case. Let's say that the molecules themselves, they're not even polar. It doesn't have to be something like water. Let's say they're non-polar molecules like, I don't know, H2 or O2, okay? Even in that case, this effect is still going to happen, and I want to show you how. All right, so now, imagine we have a whole bunch of non-polar molecules. So if there's no E field, well, basically you're going to have a bunch of non-polar molecules sitting in this region of space where there's no E field. There's going to be no separation of charge at all. Okay, so it's a pretty boring picture. But what happens when we do turn on an E field? Let's think about this. Inside of these molecules, you have electrons. Okay, and what do electrons tend to do? They're negative charges. They tend to be pulled in the opposite direction as the E field, right? So electrons in these molecules, even though they're not originally polar, are going to shift this way to the left against the E field. You see that? And when that happens, now we have a negative side where the electrons have shifted to, and we have a positive side where the electrons have left. Okay, so because the electrons are now going to be sort of biased towards this direction, now we have polar molecules. We've induced polarization, in other words. It wasn't there originally, but just by turning on this E field, now we have it. Does that make sense? All right, so any way you cut it, you're going to get this alignment of the molecules with a positive end going with the E field and a negative end going against the E field. Okay? So what we call this is the induced electric field. So we want to be very clear about what's happening. There's E naught in this picture is some outside electric field. It's an external electric field that these molecules are not creating. They're just inside of that electric field. But you can see that the molecules themselves, because they have positive and negative charges, which are separated out, they create their own electric field. Which way is it going? Well, pretty easy to see, hopefully. Remember, electric fields go from positive to negative charges, right? So this little molecule right here is creating a tiny little electric field going from positive to negative, which is this way. See that? This polar molecule up here creates a tiny little electric field, goes from positive to negative, which is that way. So whatever the case may be, whether you're dealing with polar molecules or nonpolar molecules, you induce an E field in the material that opposes your external E field. You see how the induced E field is going against the external E field? It's an important thing to see here. Okay? And that's really at the heart of what's going on in a dielectric, is you induce this E field. So let's take a closer look at that. All right, so here is a capacitor without any dielectric. So you have a positively charged plate like this, and you have a negatively charged plate like this. And what's happening is your E field is going from the positive plate to the negative plate. So I'm going to show that with black lines. So this is going to be E naught. Let's be very clear about what E naught is referring to. E naught is the E field that's just due to the charges on the capacitor plates. Okay? So it's just because of the charges on the plates, nothing else. And of course, if we have no dielectric material, that's the only thing happening. There's no other E field because it's just a vacuum in between. But when I do have a dielectric, we have that electric field that's due to the charges on the plates going from here to here. It's still shown in black. That hasn't changed. But in addition to that, we have this E field that's induced within the molecules, okay? And I'm showing that to you in red. And remember, I just explained how this is going in the opposite direction, right? So we have this induced E field, which is opposing our E naught. And really, the total electric field in between the capacitor plates is the sum total of those two E fields, right? Because you have the E field due to the charges on the plates here, and the E field due to the dielectric charges on the inside. Okay, and you have to add those together to understand what the total E field is. Does that make sense? So, overall, what do we get? A bigger or smaller E field? Yeah, it actually reduces the strength of the E field because the induced E field opposes the one you originally had. Okay, so here's what we have. E, that refers to the sum total E field, right? As I explained, E naught, that's due to the charges on the plates, and E induced is due to the dielectric molecules, okay? So because they oppose each other, the total E field is E naught minus E induced. Does that make sense? As they go against each other, we subtract. But check this out. We previously found this. I showed you before that the total E field is equal to E naught divided by K. In other words, it's reducing the strength of the E field by a factor of K. I showed this already, so hopefully that's looking familiar. Let's take these two results and work out this result here. It's actually pretty simple. Let's just do it. Where's my pen? Oh, here it is. So, here's what we have, everybody. We have E, the total E field, equals E naught, the field due just to the charges on the plates, minus E induced. And we also found that E equals E naught divided by K. So plug that in right here. We have E naught divided by K equals E naught minus E induced. So we want to solve for E induced right here. E induced is going to be equal to E naught minus E naught over K. So I can write that as E naught times 1 minus 1 over K. So this is useful because if we know the E field that's just due to the charges on the plates, all you need to know is the dielectric constant, and you can get the E field induced in those dielectric charges, okay? And that's how you calculate it right there. Any questions on that? Okay, so here, just going to summarize the result. E induced is E naught times 1 minus 1 over K. Okay, so we have these three different E fields to keep track of. One is the total, one is this one from the charges on the plates. The other is the induced charge, the induced E field, and they all relate to each other in this way. Okay. So another thing we want to talk about here is something called induced charge. So here's what's going on in this case. When we refer to Q plus Q minus Q, we're referring to the charges that are on the plates of the capacitor. So these are charges that are on the two conducting plates that make up the capacitor. But I hope you can see from this picture here that if we have a dielectric material in between the plates, that some charge is going to build up on that dielectric material itself. Okay, and let's just see how that works. Remember, these molecules are going to be oriented to face the same direction as the E field. So we're going to have positive charges going that way, negative charges going that way. And that's going to be true across the entire material. Okay, so this is going to be happening on a very, very large scale. But let's look at the very outer surface of our dielectric material over here. On this surface right here, you see there's a whole bunch of positive charges on that surface because all of the positive ends of the molecules are facing this way, so this surface is going to have a whole bunch of positive charge built up on it. And by the same token, the negative charges are going to be facing this way, so this outer surface of the dielectric is going to have a whole bunch of negative charges piling up on it. So overall, of course, there's no charge on the dielectric, but what I'm saying is there is a positive side and a negative side. Make sense? So what we're going to call that charge is Q induced, because it's the charge we induce on the dielectric material. Okay? So overall, we have plus Q, minus Q on the plates. On the dielectric material, we have plus Q induced, minus Q induced on the two sides. That's what we're dealing with here. Does that make sense? So what I'm going to show you is how do we relate the two? How do we go from the charge on the plates of the capacitor to the induced charge? So there's a formula, we'll derive it, and I'll show you how this works. Okay, so quick derivation. We already saw that the E field induced is equal to the E field just due to the charges on the plates times 1 minus 1 over K. Okay, so I want to remind you that inside of a parallel plate capacitor, the E field, okay, is given by the following. It's given by sigma divided by epsilon naught. This is something we derived way back in the first chapter, so I just want to remind you of that fact, okay? And does anyone remember what sigma represents? Yeah, it's a charge per unit area, right? So essentially we have, two of these terms to think about. One of them is due to the charges on the plates, okay? Because we have a positive plate and a negative plate, there's an E field, which is given by this formula. But also because we have a positive side of the dielectric and a negative side of the dielectric, we also have an E field induced from that. But each one of those E fields can be written in terms of this formula. So what we'll do is just plug that in. So for E induced, I'm going to have Q induced divided by A times epsilon naught. And for E naught, I'm going to have Q. That just represents the charge on the plates divided by A times epsilon naught, 1 minus 1 over K. So we can cancel out this part, and we just get Q induced equals Q times 1 over 1 minus K. So in other words, the relationship between E naught and E induced is pretty much the same as the relationship between Q and Q induced. Just multiply by this factor right here, okay? Any questions on that? So the result is, just to go back to the slide, the result is Q induced equals Q 1 minus 1 over K. All right, just a little bit of terminology here before we move on. Sometimes the charge on the plates is called the free charge, and it's called that because presumably this is part of some conductor, and that charge is free to move around within the conductor, okay? This charge that appears on the dielectric, on the surfaces of the dielectric, is often called the induced charge. Sometimes it's also called the bound charge, okay? So that's just some terminology for what we're referring to here. All right, so I think what we'll do next is this. I already went over this a little bit, but I'm going to go over it again. So what we eventually wanted to get to is why is it that dielectrics, when we place these materials in a capacitor, why is it that it increases the capacitance? Well, you can look at this from a number of different perspectives, but let's take a look at it from the perspective of keeping the charge constant, okay? and asking what happens if we keep the charge constant, what happens when we introduce a dielectric. Okay, so all of these are things we derived already. We saw that if you have a constant charge and you put a dielectric in between the plates, you reduce the voltage by this factor. V equals V naught divided by K. Okay, so we already showed that. So the idea here is, since you get the same amount of charge Q, but you reduce the voltage, you're effectively increasing the capacitance, right? Because if you look at this formula, Q over V, if you're staying the same with your Q value, but you're reducing the V value, you're increasing the C value. Okay, so in other words, capacitance is Q over V. And if what we're saying is the voltage changes by a factor of K, V equals V naught divided by K, that's what we're doing here. The K can just go straight to the top, right? Okay, so we have K times Q over V naught. But that was our capacitance initially, right? Because the charge divided by the voltage initially, before we added the dielectric, is this value right here. So we're calling that C naught. So that's why C is equal to K times C naught. Okay? As you can get the same amount of charge on the plates for less voltage, you have a greater capacitance. That's the idea. Okay? Any questions on this? All right, we're going to do an example here, and then hopefully we can get to an example where you guys work it out and solve the circuit. Okay? Let's do this one first. So here's what's going on. We have a capacitor that has two conducting plates. Each one has an area of 0.125 square meters, separated by a tiny distance. D equals 0.0150 millimeters. The space between the plates is filled with the dielectric, where the K value is 20. And we connect it to a battery where the voltage is 300 volts. So we're going to do a whole bunch of calculations. We're going to calculate the capacitance of this capacitor here. We're going to calculate the charge on the plates. We're going to calculate the induced charge on the surface of the dielectric. We're going to calculate the total E field. We're going to calculate the electric field due to just the charges on the plates. And we're also going to calculate the induced E field. So basically, we're going to use every single formula that we derived today in this problem, okay? You ready? All right, let's do it. So let's find the capacitance first. Let's do that. So we'll find the capacitance. For this, we're going to use C equals K times C naught because we are dealing with a dielectric material. But we have a parallel plate capacitor, and we know the formula for C naught is A epsilon naught divided by D. So we just take that and multiply by our dielectric constant to get the capacitance. So here's what we have. K is 20. The area is 0.125 square meters. Epsilon naught is 8.85, 10 to the minus 12. And we can think of the units as farads per meter, if you recall. The distance between the plates is 0.0150 millimeters, so that's 10 to the minus 3 meters. Can someone work this out for me? What does that come out to?
One point 47 times 10 to the negative 6.
Yeah, So 1.475, keep 3 sig figs, 10 to the minus 6 farads, which we can write that as 1.48 microfarads. Okay? All right, so next, let's find the charge on the plates. Now this is relatively straightforward. Q is equal to C times V. We know the capacitance and we know the voltage across the plates, which is determined by the battery we attach it to. We know the charge on the plates. So this is going to be the C value, which we found, 1.475, 10 to the minus 6. Farads are coulombs per volt. And we're multiplying by 300 volts. That makes sense? So what does this come out to? Just take the previous answer times 300.
4.42 times 10 to the negative 4.
Yeah, so 4.425, we get 10 to the minus 4, right?
Yeah.
Coulombs. So you could write that as 443 microcoulombs. That'll work. Okay. Now, that's the charge on the plates. The induced charge, I mean, to be clear, what we're talking about here is the charge that's induced on the two surfaces of the dielectric, but we know how to calculate this from our derivation before. Q induced equals Q, 1 minus 1 over K. So that's going to be 4.425, 10 to the minus 4 coulombs, that's Q, times 1 minus 1 over 20, which is K. What does that come out to?
$4.20 times 10 to the negative 4.
10 to the minus 4 coulombs, 420 microcoulombs. Okay? Right, let's do some other stuff. The total E field. Let's get that. Well, remember we worked this out earlier, but if we calculate the potential difference from one plate of the capacitor to the other, that's given by E times D. So the total E field that we're integrating over to get this result is E, and we can find it by just taking the voltage divided by the distance. Okay? And again, the voltage is 300 volts. The distance is the tiny little gap, in this case, between the plates of 0.0150 millimeters, which is 10 to the minus 3 meters. Can someone tell me what that works out to?
Times 10 to the 7.
Yeah, so 2 10 to the 7 volts per meter. We could also express that as 2 10 to the 7 newtons per coulomb. That is the total E field in between the plates. But remember, this total E field can be broken into two parts. It's the E field due to the charges on the plates and the E field due to your dielectric material combined, right? So that's the total. Now let's figure out how to go from the total to each individual piece, okay? So the E field due to the charges on the plates, this is what we call E naught. So what we found before is E, the total E field, is equal to E naught divided by K, right? So if we want to use that to solve for E naught, that's going to be E times K, okay? So that's going to be 2.00, 10 to the 7 newtons per coulomb times K, which is 20. So that's that's just going to be 4 10 to the 8. Remember, we do expect that the total E field is less than the E field just due to the charges on the plates. Because the E field due to the charges on the plates is counteracted by another E field, right? So it makes sense that these values shake out in that way. So the last thing we're going to calculate is E field induced in the dielectric. So this is what we call E induced. And we worked out a formula for this as well, which is E naught times 1 minus 1 over K. Okay? So E naught is what we just found, 4 times 10 to the 8 newtons per coulomb. And then we have 1 minus 1 over 20. What does that work out to?
Times 10 to the 8.
That's right. Okay, so these two E fields, which are counteracting each other, add together to give you this total E field. That's what's going on here. Okay? So basically, I think we used all the formulas we derived that describe dielectrics. So there's another example like this in the practice problems, but I think this pretty much covers it, okay? So do we have any questions on that?
So like the total E field equals the E field due to the plates
Minus this one.
that. Can we just subtract them?
Yep, you can do that. You can subtract this from this and you'll get this. It works out that way, yeah. Anything else? All right, so we have time for a problem, and I think the best use of the time is to do something like this, where we have some kind of circuit involving multiple capacitors, and we solve that circuit in order to find the charge on each one of the capacitors. So here, let's do this one, all right? Here we have a battery that provides a voltage of 12 volts to our circuit. All the capacitors are identical. They all have the same C value of 550 microfarads. So we're going to do a couple things. First, we're going to find the equivalent capacitance of this set of 5 capacitors here. And then we're going to find the charge on each one. So this is similar to the first problem we did today. So let's get working on this, but I want to make sure we're all on the same page as far as how would we combine all these capacitors into a single one. What would we do first?
Is C3 and C4 in series?
They're in series, but it's more than just that. What else?
C2 is equal to 5, right?
2, 3, 4, and 5, they're all in series because they're connected along a single conducting path. These are all in series. So start with that. Combine all 4 of these together. Then once you've done that, what would the next step be? Yeah, then this entire combination would be in parallel to C1. And then you combine those two, and now you're down to 1 capacitor, and that's how you can solve this, okay? So start with that, try to get the equivalent capacitance, and then we'll reconvene once you have that answer, okay? So take about 5 minutes to work out the equivalent capacitance. what I would do as you go through this is redraw the circuit each time you combine capacitors. It's really gonna help you keep track of things as you go on. That's correct, tell you. Saw a few of you have the answer for the equivalent capacitance. Does anyone want to say what they got?
Is it 66.5?
You should be getting 62.5, okay? So for the rest of this problem, let's work it out together to get the charges, okay? Because this takes a little more work, but let's go through it. Right, so everybody, we're gonna start by combining 2, 3, and 4, and 5 in series. That's the first step we're gonna take, okay? So C2, C3, C4, and C5 are in series. So how do I find the equivalent capacitance of C2, 3, 4, 5? If I combine these into one, how does that go? Yeah, so for series capacitors, the idea is you take 1 over each C value. But then you have to take that to the -1 power, okay? That's how this works. So basically, we're just dealing with 1 over 50 plus 1 over 50 plus 1 over 50 plus 1 over 50 to the -1 power, which is just 4 over 50 to the -1 power because we have 4 terms, which is 50 over 4. And 50 over 4 is what? That's 12.5 microfarads, correct. Okay. The next thing to deal with here, we haven't combined everything yet, but when we have capacitors in series, what can we say about the charges? Charges are equal. So, Q2 is equal to Q3, is equal to Q4, is equal to Q5. Because these are all in series, they have the same charge. And that's equivalent to the charge on our equivalent capacitor Q2, 3, 4, 5. Okay? So what we're going to do next is redraw the circuit from the original drawing. So now we have just 2 capacitors in our network. We have the battery here. We have capacitor C1, which we haven't dealt with yet. But in this branch of the circuit, we've combined everything. into a single capacitor C2345 like this. And now let's actually label the charges. This is going to help us see what comes next. So on this capacitor, I have positive and negative Q1. On this one, I have positive Q2345, negative Q2345 on those plates. Okay? So we good so far? All right, so what can we say about these two capacitors? C1, C2345. What type of connection do they have to each other? They're in parallel. Okay, so actually, what's the rule for combining capacitors in parallel as far as how we add the C values together?
Just add them.
It's just straight addition, right? We don't have to deal with the inverses. So C1, 2, 3, 4, 5, that's all of them combined. It's just equal to C1 plus C2, 3, 4, 5, correct? What's C1? Yep, they're all 50 microfarads. And C2, 3, 4, 5 is 12.5 microfarads. So that's where this 62.5 microfarad equivalent capacitance came from. Okay? Okay, but just like before, we're going to want to relate these charges to each other. So any idea how we can do that? When we're in parallel, charges are what?
Equal.
They're not equal. They add together. Charges add together. So here's the logic behind this. I want to make sure you see what's going on here. When I write Q1, 2, 3, 4, 5, that's kind of a lot to write. But basically, that's just the total amount of charge from the battery going into these two combined. See, the charge doesn't just go down one path. It splits into two paths. Some of it goes this way and charges up this capacitor. Another part of it goes this way, charges up this capacitor. So the total is the sum of these two. That's just conservation of charge. Total amount going into this branch is the sum of these two. So we have Q1 plus Q2, 3, 4, 5. Does that make sense? What can we say about voltages? Yeah, voltages are equal when it comes to parallel components of a circuit. So that means V1 equals V2, 3, 4, 5. And what we're trying to solve for is charge. So remember, how do I write the voltage across a capacitor in terms of the charge on it?
Q over C.
It's Q over C. So I have Q1 over C1 equals Q2, 3, 4, 5 over C2, 3, 4, 5. I know it's a lot to write all these subscripts out, but trust me, if you don't keep track of this stuff, it's going to be hard to get the right answer, okay? So let's take that and solve for Q2, 3, 4, 5. That's going to be equal to C2, 3, 4, 5 over C1 times Q1. And this right here, the C2, 3, 4, 5 was 12.5 microfarads, whereas C1 was 50. So what's 12.5 over 50? That's just a nice fraction, 1/4. So this charge, Q2, 3, 4, 5, is a quarter of Q1. That's what we found. Does that make sense? Okay. So let's at this point just redraw the circuit one more time. So now we just have one battery connected to one capacitor, which is a pretty simple situation. C1, 2, 3, 4, 5 with charge Q 1, 2, 3, 4, 5 on it, plus and minus. If you don't want to write all those subscripts out, you could just say CEQ, but I'm going to do it this way, okay? So how do I find that total charge Q 1, 2, 3, 4, 5? Yeah, because that would just be the capacitance times the voltage for my combined capacitance. C 1, 2, 3, 4, 5 times V. Does that make sense? Okay. And this combined capacitance of all five is 62.5 microfarads, which is 10 to the minus 6 coulombs per volt. 12 volts was our voltage. So what does this equal?
Times 10 to the negative 3.
I'm getting
Negative 4.
yeah, I'm getting negative 4 as well. 7.5, 10 to the negative 4 coulombs. Okay. All right, so here's what we're going to do next, all right? I'm going to take this equation right here, which says Q1, 2, 3, 4, 5 equals Q1 plus Q2, 3, 4, 5. But for that second charge, I'm going to replace that with a quarter Q1. Does that make sense? So if you look at these two equations, I can sub in 1/4 Q1 right here. And that gives me Q1, 2, 3, 4, 5 equals Q1 plus a quarter Q1. And that's just the same as saying 5/4 Q1, right? Which means Q1 is 4/5 of Q1, 2, 3, 4, 5. Make sense? So take 4/5 of what we just found, and what do you get?
6 times 10 to the negative.
Yeah, that's just 6 10 to the minus 4 coulombs. Okay? Okay, let's do the rest. So going actually up to the very top of this page, when we were dealing with the series connections, Q2, 3, 4, 5 is the same as individual values of Q2, Q3, Q4, and Q5. Okay? And that's just a quarter of Q1. Okay? Does that make sense? So all of those individual charges of 2, 3, 4, and 5 are the same. And they're equal to 1/4 of Q1. So that's 1/4 of what we just found, which is 6 10 to the 4 coulombs. What does that give us?
1.5 times 10 to the negative 4.
I should have said negative 4. 1.5 10 to the negative 4 coulombs. Okay, so that's the result. 2, 3, 4, and 5 all have this much charge, 1.5 10 to the negative 4 coulombs, and then Q1 has this much charge, 6 10 to the negative 4 coulombs. So we've solved the entire circuit by combining things in parallel and series. Okay? So that's it for today. See you next time.